Yeah, I think that the future will explore the universe as part biological and part computer.
What if there are something even more exotic than stars, galaxies, and infinite space in reality? A massive quantum computer, a massive cosmic algorithm that has been in operation for more than 13.8 billion years, is made up of every particle collision, light flash, and even your thoughts. Physicists are currently studying a mind-bending notion. The universe contains more than just information. Every second is calculated. Information is what it is. Every atom has a unique code. You do play a part in the finished result, in fact. Are you prepared to fall down the rabbit hole of quantum? Reevaluating the universe's nature. Many of us grew up thinking that the universe is a vast empty expanse filled with stars, galaxies, and swirling gas clouds. We may consider matter and energy to be the basic building blocks of everything. When atoms are dropped, gravity pulls them downward. When you strike a match, it flames. Planets orbit stars, which are powered by fuel consumed in their centers. This well-known hypothesis holds that the universe operates like a huge physical machine that complies with accepted laws. Even while this graphic is useful, some scientists now argue that it might not accurately depict reality. A new idea in modern computer science and physics suggests that information could actually be the basis of reality. Instead than viewing the universe as lumps of material moving through space and time, another viewpoint maintains that everything that happens, from a photon hitting your eye to a black hole swallowing a star, is the product of information processing. The physicist John Wheeler famously summed up this point of view in 3 short sentences. It was a small source. This suggests that items that appear solid and obvious may actually be the product of underlying information. But what does it mean to imply that the universe may operate like a quantum computer? When people hear the word computer, they frequently picture a large server, a laptop, or a phone, all of which were built by humans. We create the programs or instructions that these machines follow. They may be connected into an electrical outlet or run on batteries. The notion that the entire universe is a computer does not imply giant wires or a cosmic programmer clicking run. Instead, it raises the possibility that our universe is constantly processing quantum information. It's possible that every particle interaction and event we observe is part of an ongoing calculation that has been occurring since the beginning of time. If this hypothesis is right, then everything, matter and energy, space and time, life and consciousness, would be the outcome of that complex quantum computation. This hypothesis differs from a typical simulation hypothesis in that there is no external machine. At this moment, we are not in a simulation. Rather, the universe itself functions by the principles of a quantum system and exhibits computer-like behavior. It's possible that the digital processes we observe in labs, such as bits or qubits changing states, are actually a small representation of the billions of years that the cosmos has been going through. This may come as a surprise, yet it is consistent with other puzzling findings in theoretical physics. Instead of being seen as the background stage on which events occur, space-time may be the outcome of profound entanglements of quantum bits. Instead of seeing black holes as simple gravitational drains, we may see them as extreme places where information is distorted and confused. All of this suggests that rather than viewing the world as a simple emptiness full of objects, it could be good to look into the idea that it is a global process that is constantly changing by flipping, storing, and moving bits of data in ways that we are only now starting to grasp. Bits become crucial. To understand why some scientists place a higher value on information than on physical substance, consider the role that information plays in every physical event. What if a single particle, like a photon, has both energy and certain properties? Direction, polarization, and wavelength. These properties essentially give information on the photon and how it was created. When it comes into touch with an atom, it may either convey or change that information. During this process, the atom's state is altered. On a larger scale, light from particle collisions in the center of a star travels across space and eventually reaches observatories on Earth, where it provides information about distant cosmic events. Physicists say there is never any real loss of information. Quantum theory states that even in the most dire situations, such matter collapsing into a black hole, information must somehow survive in the universe. Information's refusal to vanish is one of the reasons it is regarded as a fundamental aspect of reality. If matter and energy could disintegrate, several physics rules would be broken. But they don't, they transform into other shapes. Information also evolves, but never really vanishes. John Wheeler's phrase, "it from bit," is more than just a cliche. The idea that information is more basic than matter and energy is strongly questioned. It is possible that what a particle or system can and cannot do is determined by bits, states, and numbers. Think about a computer. Even though it comprises real chips and cables, the end output is patterns of bits that follow logical laws. Wheeler and others elaborated on this analogy. What if physical rules like gravity or electromagnetism are the basic reasons for how pieces of reality may flip, mix, and spread? This notion leads to a related claim. There are limitations on the universe's capacity to process and store information. Physicists like Jacob Bekenstein have shown that a patch of space can only hold so much data before exploding into a black hole. This is known as the Bekenstein limit, which asserts that the amount of data that can be stored depends more on the area around a region than on its volume. This discovery is noteworthy because it suggests that the quantity of data that can fit on surfaces limits what we see and experience. The concept of holography extends beyond that. It implies that all of the information about events in a region may be stored on the limits of the territory, much as how a 3D image may be placed on a 2D hologram. This has led many people to conclude that the universe is a holographic structure composed of quantum bits. In other words, some contend that rather than seeing an endless amount of matter contained within a massive three-dimensional region, what we perceive as space is only a projection of data stored elsewhere. By focusing on information, these theories blend the languages of physics and computers. This does not diminish the strangeness or beauty of the planet. Instead, it offers a novel viewpoint by flipping the traditional order, such that knowledge becomes the focal point, and matter and energy are the result. What makes quantum so crucial? One could ask, why not a conventional computer world? Why specifically a quantum computer? The answer lies in the characteristics of particles at minuscule sizes. Traditional or classical computing is built on bits, which can be either 0 or 1. However, a condition called a superposition allows qubits in a quantum system to be both 0 and 1 at the same time. Unlike a regular bit, which is just on or off, a qubit may hold two states in parallel until it is measured. Another option made feasible by quantum physics is entanglement, a situation in which two or more qubits become coupled to the point where knowing the state of one influences the state of the other, even if they are very far apart. Spooky action at a distance is how Albert Einstein described this phenomenon. As we now know, several experiments have verified that it is authentic. This entanglement is also substantially responsible for the fact that quantum computers can solve some problems far faster than conventional machines. Quantum theory states that measurement modifies the state of the item being measured. Prior to measurement, a particle may be in a variety of outcomes, but upon measurement, it compresses to a single result. This collapse basically happens when the system uses quantum probability to choose a result. Importantly, the entire mathematical basis of these events may be seen as an information process. Wave functions hold the information about possible outcomes. Interactions scatter or jumble this data, and measurement completes it. Assume that these principles fundamentally apply to every particle in the cosmos. Unlike us in everyday life, they don't act like tiny billiard balls, pushing each other about. Instead, they follow the quantum mechanical laws of probability. With this view, the universe no longer operates like a gigantic clockwork. Rather, it is like a massive quantum computer that is continuously doing these probability updates, entangling and disentangling states, and collapsing states based on interactions or observations. Researchers and labs are using the same quantum rule to build functional quantum computers. Their devices are not only quantum physics simulators, they're living it out. This suggests that the best model for the behavior of physically small systems is not a classical collection of logic gates, but rather a quantum set of gates that govern kits. Furthermore, if nature is indeed quantum mechanical, rather than just a theoretical idea, then seeing the universe as a huge quantum processor makes sense. Holographic boundaries. One of the strongest reasons for a deeply developed universe is the way science treats black holes. Stephen Hawking found that black holes are not entirely black. They eventually disappeared due to the discharge of what is called Hawking radiation. This leads to a big dilemma. If the data that is trapped within a black hole eventually disappears, what will happen to it? Quantum. Physics states that information cannot just vanish into thin air. This conundrum is known as the black hole information paradox. For many years, physicists were unsure if black holes were destroying information or if something else was taking place. Black holes are thought to have the potential to confuse incoming data. Instead of destroying it, they release it as Hawking radiation in a severely distorted form. An unusual quantum system that jumbles and processes information inside an event horizon before releasing it gradually over eons is analogous to a black hole in this regard. Another key idea is the holographic principle, which was partially proposed by physicists Leonard Susskind and Gerard Tufte. It asserts that all of the information concerning the event horizon, a region of space that mimics the inside of a black hole, may be contained within it. If you can read the encoding on that border, then theoretically you know everything that's within. This is like preserving a 3D image on a 2D film. The movie alone contains all the information required to rebuild the whole 3D object. Thus, the black hole surface is the primary element, influencing the total amount of information it can store. The entire cosmos has been expanded to the possibility that our entire three-dimensional reality may resemble a holographic projection from a distant two-dimensional surface, often called the edge of the cosmos or a barrier at infinity. Even while we might never be able to see it with our own eyes, the math suggests that this barrier might be the ultimate hard drive that contains the data describing everything in the universe. By seeing black holes as quantum information rather than just gravitational collapse, we may further combine general relativity and quantum physics. The topic of the black hole changed from being only about mass and gravity to being about where, how to retrieve data that has been modified and stored. The combination of the hitherto separate fields of information theory, quantum physics, and gravitational studies reinforced the notion that the entire universe is a continuous program that stores and processes data on boundaries and across space-time, creating space-time with quantum entanglement. If the universe is indeed processing quantum information, we could wonder how space-time itself is created. In traditional physics, space-time is the basic stage on which events occur. Some academics, however, contend that space-time is not necessary. Instead, it might originate from networks of entangled quantum bits. The geometry of space. The distance between sites depends on how these qubits are connected. Think about a big qubit network. When many qubits tangle with each other, a kind of fabric is produced. The more intertwined they are, the closer they may appear in the effective geometry. As the entanglement decreases, they become more haphazard. Despite the speculative nature of this, scientists use rigorous mathematical techniques, such as tensor networks, to describe these notions. These networks, like A, which stands for multi-scale entanglement renormalization and satellites, show that in some cases, a lattice of qubits may give a geometry that is quite similar to the curved space-time we study in general relativity. In order to build dependable quantum computers, the technique also pertains to quantum error correction. In error correction, information is spread across many qubits such that even if one qubit is disturbed, the entire quantity of information may still be recovered. Remarkably, several theoretical physicists discovered that, especially in models like anti-Sitter space, CFT, and conventional field theory, some representations of spacing may be understood as quantum error correcting codes. This implies that in addition to perhaps originating from quantum entanglement, space-time may also have an innate mechanism for information retention. Even if a portion of space is damaged or destroyed, the geometry can still retain the crucial information. This explains why black holes do not permanently destroy information, just like a quantum error correcting approach protects qubits in a lab. Information is never really lost. Instead, it is only entangled in a more complex web from which it is hard to escape. Our knowledge of the universe is greatly expanded by these ideas. As a result of algebraic operations, spacetime changes from a static backdrop through which matter moves to an active participant. As these processes continue, distances, shapes, and gravitational effects cease to be fixed givens and instead become emergent properties. Researchers think that this method, which integrates Einstein's relativity and quantum physics into a single conceptual and computational framework, might result in a theory of everything. Emergent codes or preset guidelines. Physics lectures cover a variety of subjects, including gravity, electromagnetism, immutable laws, and the strong and weak nuclear forces. To us, they are indispensable. But if the universe is a quantum computer, these laws may be emergent principles that come from deeper patterns of information processing. In other words, the laws we measure might be the stable, long-term results of bits flipping and spreading over the universe. Consider the emergent behavior that occasionally occurs in software. Allowing a complex system, such a simulation with several interacting components, to function may result in the emergence of certain persistent patterns. Many patterns act consistently and may be described by simpler principles, even when they originate from more complex underlying code. In a similar vein, stable phenomena like gravity and electromagnetism could originate from the underlying quantum logic that regulates the smallest scale, such as near a black hole or in the early universe. We could find changes that are different from our typical legislation because we are looking at levels of the code that are rarely observed at ordinary energies or distances. Other sections of a possibly bigger quantum universe, which some have named a multiverse, may be governed by distinct sets of rules, such as different values for the speed of light or the many coupling constants that characterize how forces behave. There is just one region with a single, consistent set of laws. There, quantum states and entanglements lock in a certain pattern early on, forming a stable code that can work for billions of years, creating stars, planets, and eventually life. The question of energy also arises in this situation. Labor capability has always been linked to energy. In an enlightening universe, energy may also be thought of as a measurement of the quantity of computations that can be made. Bits must be processed or erased using energy. If the cosmic code is working, then just a portion of the initial cosmic supply of ordered states is being consumed. Similar to a battery that eventually runs out of power, thermodynamics, and particularly the second law, entropy grows, may also be interpreted in terms of information. Entropy may be used to quantify the degree of data jumbledness, or the number of states that a system may occupy. Over time, energy and complexity increase as the system explores more states. Instead of seeing the laws of physics as rigid instructions, these concepts inspire us to see them as the emergent logic of how quantum information organizes itself under particular constraints, complexity, life, and consciousness. If the universe is a quantum information process, what function does life serve? How did chemistry, DNA, and eventually sentient brains develop from a set of flipping qubits and newly discovered natural laws? Many people think that complex systems develop organically in environments with a plethora of information. Layers of complexity can rise wherever there are rules that allow for stable structures and feedback loops. Life is one of the most exquisite examples of complexity. Cells duplicate themselves to create organized structures from simple materials. Environments where matter and energy flowed and interacted vigorously are where life on Earth first began. Over millions or billions of years, random mutations that improved survival were locked in by natural selection. One may consider those changes to be information encoded in DNA. An organism's success in its environment is influenced by its genetic code's capacity to compute solutions for reproduction and survival. If the universe were a quantum computer, life would be one of its local programs that also modifies that part of the code, sometimes in a big way, like in the case of people. Awareness, which is far more difficult to articulate, arises from life. But in an information-based universe, consciousness may be viewed as an extra layer of data processing. The brain's many neurons translate sensory data into internal representations, make decisions by integrating this data with your past experiences. Some scientists argue that quantum processes in the brain could be important, whereas others think conventional mechanisms are adequate. At any rate, awareness becomes a real and rare thing, a structure that can mirror the universe in itself. This capacity for self-awareness, especially if it entails knowledge of cosmic rules, may be a distinct emergent layer of quantum computing in general. Therefore, observers ask if the universe operates as a quantum computer. Could it be part of the cosmic code's natural unfolding? The code is observing and trying to use brains to decode itself. It may not be cosmically purposeful, the universe may not have an intrinsic purpose, but this is still a magnificent result. It suggests that we as conscious beings are a representation of the universe's ability to understand its own fundamental logic. Limits of simulation. Can we use a smaller quantum computer to duplicate the entire thing in a lab if reality is a massive quantum computer? Scientists are already employing quantum computers to represent small quantum systems, such molecules or groups of interacting particles. These simulations have enormous potential for fields including chemistry, material science, and cryptography. However, the idea of modeling the entire universe from within is hindered by fundamental issues. The first principle is that a system cannot fully model itself without exhausting all of its resources. To build a computer that replicates the universe in its entirety, you would need at least as many qubits as the universe itself. Since your simulator is a component of that same universe, it is unable to transcend the cosmic boundary. This relates to self-referential limits in computer science. No finite machine could have a detailed blueprint of itself, as the map would have to be at least as large as the territory it represented. Secondly, thermodynamics imposes restrictions. Information is stored and deleted using energy. It would take a tremendous amount of energy to replicate everything, maybe more than the universe can provide in any one location. Furthermore, even if such energy were available, you would still run into the Beacon-Stein bound, the most info that can be stored in a certain area. Third, true quantum processes are often described as computationally irreducible, meaning that future events can only be predicted by allowing the system to grow. In complex or chaotic systems, you can't just skip steps. You must follow each link in the chain. This makes it difficult to predict the weather more than a few weeks ahead of time. It might mean that the universe is the only machine large enough to do quantum computations in real time. Therefore, while partial simulations used for certain purposes are helpful tools, the goal of producing a perfect, smaller-scale reproduction of the entire universe remains impossible. However, from an educational standpoint, we don't need a complete simulation to understand the rules. We are capable of breaking out code segments, identifying patterns, and testing them. Physicists have always done this. They simplify reality to get useful formulae, which are then confirmed in laboratories. This approach is different because it considers the fundamental language to be quantum information rather than just traditional mathematics. Entropy, heat, death, and a slow cosmic fading. If it happens, will the universe still compute? We often find that entropy increases with time, meaning that each activity increases the overall disorder in the ecosystem. From an informational perspective, this may be seen as the system exploring a growing number of possible states. A state known as heat death, in which the temperature is almost constant everywhere and there is no more usable energy to enable further computations, may someday occur throughout the universe. Galaxies and living organisms are examples of organized systems that cannot be sustained in the absence of new energy flows. Black holes evaporate over extraordinarily long periods of time, stars burn away, and so on. Without new energy inequalities, the universal program has nowhere to go. It either gets stationary or slows down to the point that it might as well be repeating the same boring pattern. This might mean that there is no more room for meaningful evolution of the cosmic code. No significant changes are anticipated to take place, although there could still be some data scattered across the ruins of the cosmos in stable forms. As a result, the universe is denied the chance to generate new patterns or store new information, becoming a silent field of homogeneous radiation or spent matter ashes that still follow the quantum norm. The calculation would effectively stop even if it is not entirely off. Random quantum fluctuations may sometimes ignite new pockets of complexity, according to certain bold theories, such as the idea of Boltzmann brains, brief cognizant lumps that suddenly appear by mistake. Such events, however, would be incredibly rare, irregular, and transient, offering no sign of a new cosmic era. The underlying quantum vacuum that underpins our daily world may alter, rewriting the laws of physics and maybe beginning the cosmic computation in a different way, according to hypotheses of a potential phase transition or vacuum decay. This might result in the development of completely new complexity conditions. The main notion is that despite the fact that this is entirely hypothetical and not guaranteed, any continuous computing system requires a supply of free energy and a method to retain state differences. As entropy rises, that supply decreases. The cosmos is racing to equilibrium. Moreover, once the universal quantum computer is delivered, it will not need to do any more calculations. For now, though, we are living in a period of bright stars and active processes that are pulsing with energy. We may view this time as a special window for complexity and life to flourish as part of the larger cosmic code. Thank you for watching another episode. Click the video on your screen while you are still here for better quality content.